This video will demonstrate how to design a double angle bolted welded connection in VAConnect. Let's get started. In this example, we will design double angles bolted at the column and welded to the beam to connect the web of a W16 by 36 to the flange of a W14 by 90 as shown in the detail. This connection will be designed to resist both shear from dead and live loads and axial loads in both tension and compression from wind. VAConnect accounts for the interaction of shear and axial load in bolted welded double angle connections by following the procedure outlined in the AISC Steel Construction Manual Part 12, which is new to the 16th edition of the manual. In VAConnect, double angle bolted welded connections are checked per the AISC 360 design specification and follows Part 10 and Part 12 of the AISC Steel Construction Manual. The eccentricity on the supported side of the double angle connection, that is the beam side, is considered using the instantaneous center of rotation method to determine the eccentric weld group capacity at the beam side of the double angle and at the web of the beam. The C coefficient for eccentrically loaded weld groups are included in the detailed reports. Note, VAConnect assumes that the pin, which allows for rotational ductility, occurs at the face of the support. Therefore, eccentricity at the faying surface of the double angles and the support is not considered. We will start out in VAConnect by adjusting the geometry of the connection. Selecting the beam, a W16 by 36 will be chosen from the shape database. Next, we will adjust the thickness of the support equal to the flange thickness of the W14 by 90 column. Selecting the double angle shows that two 5 by 3.5 by 1/4 inch angles are used by default. Let's adjust the number of bolt rows to 3 starting out. Now we can move on to applying load to the connection. We will enter the values for shear in the dead and the live load cases, and then enter values for wind load in tension in one service case, and wind load and compression in another service case. With the surface loads defined, we can go on to the load case manager and select which building code we want to use for the load combinations, which are automatically implemented. Now with the loads and load combinations specified for the connection, we can turn our attention to the project status to see all the limit states that are automatically checked. Immediately, we see that several limit states are failing. The double angles are failing in shear yield and shear rupture and in block shear. Additionally, the bolts are failing in combined tension and shear with prying at the support. The first thing we'll do is increase the thickness of the angles, which resolves the failure limit states for the double angles, but we see that our bolts are still failing at the support. To try and resolve this issue, let's increase the bolt rows to 4. Now the bolt tension with shear and prying limit state is failing with a unity value of 1.1. Clicking on this limit state shows that the alpha prime factor is greater than 1, which means that the fitting has insufficient strength to develop the full bolt available tensile strength. As a result, simply increasing the bolt strength will not cause the unity value to decrease. To increase the capacity of the connection, we need to increase the Q reduction factor for prying, which we can do by further increasing the thickness of the angles. After making this adjustment, the combined bolt tension and shear with prying limit state passes. It is also worth noting that in this limit state, the nominal tensile stress of the bolts were modified to include the effects of shear stress. In this case, the nominal tensile strength of 90 kSi was reduced to 81.8 kSi to account for bolt shear. Now all of the active limit states for the connection pass, and we have no detailed warnings, meaning that the connection is adequate to support the applied loads. Note, the flexural yield buckling limit state and the flexural rupture limit states for the double angles are currently checked because eccentricity on the beam side of the connection is always considered since the angles are welded to the web. The unity values for these checks are very small since we only have a half-inch offset from the support to the web of the beam. If the angles had larger legs on the beam side and the beam had a larger offset, the flexural limit states for the angles would increase. The flexural demand for this connection is also accounted for in the interaction limit states, which consider combined shear, axial, and flexural loads on the legs of the angles that are connected to the beam. VAConnect also allows for one or both of the flanges of the supported beam to be coped if, for example, we wanted to accommodate a bolted welded double angle beam to girder connection as shown in this detail. The specifics of coped beams are discussed in more details towards the end of the Shear tab training video. With the design complete, we can switch to the report view to easily create a report to document our work. A concise design summary is automatically generated, showing the maximum demand to capacity ratio or unity value for each limit state. Also, information on the model and loads can be included in the report. Detailed reports that show the calculations for each limit state can be added to the report. Also, summary tables for each limit state can be included in the report to show the values of various parameters for the limit state and to show the unity value for each load set and load combination. In just a few minutes, we have used VAConnect to create an optimal design for our double angle bolted welded connection and produce a report to document our work. Thanks for watching and have a great day.